21st of July, 1942. The fog hung thick over Akutan Island like a shroud of secrecy, concealing what would become one of the most significant intelligence coups of the Pacific War. Flight Petty Officer Tadayoshi Koga never imagined his final mission would hand the Americans the key to defeating Japan's most feared weapon, the Mitsubishi A6M-0 fighter. The young pilot's Zero lay crumpled in the Aleutian muskeg, its propeller bent backward like broken fingers, its belly torn open by the soft earth that had betrayed him. Koga himself hung lifeless in the cockpit, his neck snapped upon impact when the aircraft flipped during what should have been a routine emergency landing. The Americans, hunting through the islands after the Battle of Midway, stumbled upon the wreckage 5 weeks later. What they found was nearly intact, a technological marvel that had terrorized Allied pilots from Pearl Harbor to the Coral Sea. Navy personnel immediately recognized the treasure before them. For months, Allied intelligence had pieced together fragmentary reports about the Zero's capabilities from terrified pilots who survived encounters with the nimble fighter. They spoke of an aircraft that could outturn, outclimb, and outmaneuver anything in the American arsenal. Some claimed it violated the laws of physics. Others whispered that Japanese metallurgy had achieved something the West couldn't comprehend. Now, lying in the Aleutian mud, was the opportunity to separate myth from reality. The recovery operation began with urgency bordering on desperation. Lieutenant William Thies oversaw the salvage effort, coordinating a team that carefully dismantled the aircraft and transported it piece by piece through treacherous terrain. Every component, from the Sakai radial engine to the gossamer-thin wing panels, was catalogued, crated, and shipped south. The Zero's construction astonished the American engineers who first examined it. The aircraft weighed barely 2 tons fully loaded, achieved through ruthless weight-saving measures that sacrificed pilot protection for performance. By September of 1942, the salvaged Zero arrived at Naval Air Station North Island in San Diego, California. A team of mechanics worked around the clock, reassembling the fighter with painstaking precision. They fabricated replacement parts for damaged components, matched paint colors, and even replicated the distinctive red Hinomaru circles on the fuselage and wings. Within weeks, the enemy fighter sat on American soil, ready to fly again, this time with a U.S. Navy roundel hastily painted over its Japanese markings. According to declassified Navy documents from the National Archives, the captured Zero was designated Koga's Zero, in honor of its deceased pilot, though officially it carried the technical identification of Airframe 5714. The intelligence value of this single aircraft cannot be overstated. American tacticians had spent the war's first year developing countermeasures against an enemy they barely understood. Now they possessed the enemy itself, ready to reveal every strength and, more crucially, every weakness built into its elegant but fragile airframe. The stage was set for a series of test flights that would fundamentally alter the aerial war in the Pacific. The man chosen to unlock the Zero's secrets was a pilot whose skills and nerve had already earned him legendary status among naval aviators, though even he couldn't predict the deadly flaw hiding within the Zero's control system, waiting to manifest at high speeds. Lieutenant Commander Edward Henry Butch O'Hare stood before the reassembled Zero with the practiced eye of a man who had survived more combat than most pilots ever see. Fresh from receiving the Medal of Honor for single-handedly defending the carrier Lexington against Japanese bombers earlier that year, O'Hare represented the Navy's finest. But he wasn't the only pilot assigned to evaluate Koga's prize. The actual test pilot selected for the initial evaluation flights was Commander Frederick Trapnell, the Navy's chief test pilot, and a man whose experience with experimental aircraft was unmatched in the service. Trapnell had logged thousands of hours testing everything from lumbering patrol bombers to nimble fighters, earning a reputation for analytical precision and unshakable calm under pressure. His reports could make or break an aircraft program, and now the Navy tasked him with dissecting the Zero's capabilities with scientific rigor. Trapnell approached the assignment with characteristic thoroughness. Before climbing into the cockpit, he spent days studying every aspect of the Zero's construction. He examined the wing structure, noting how the engineers had achieved remarkable strength-to-weight ratios through clever internal bracing. He studied the control surfaces, observing the large ailerons and the peculiar balance tabs that gave the Zero its legendary maneuverability. Most importantly, He scrutinized the control stick mechanism, the direct link between pilot intention and aircraft response. The first flight was scheduled for 28th of September, 1942, at North Island. Trapnell settled into the Zero's cockpit, immediately noting how cramped the space felt compared to American fighters. The Japanese had designed it for smaller pilots, and at 6 feet tall, Trapnell found his knees nearly touching the instrument panel. The controls felt light, almost delicate, a stark contrast to the heavy, authoritative feel of a Grumman Wildcat stick. Engine start was unremarkable. The Sakai 14-cylinder radial coughed to life with a distinctive bark, settling into a smooth idle that belied its 950 horsepower output. Trapnell performed his pre-flight checks with meticulous care, aware that dozens of engineers, intelligence officers, and fellow pilots watched from the tarmac. This wasn't merely a test flight, it was an intelligence operation with potentially war-winning implications. The takeoff roll was astonishingly short. The Zero leaped into the air after barely 300 feet, climbing at an angle that would have stalled most American fighters. Trapnell felt the aircraft respond to the slightest control input, the ailerons providing crisp roll response even at low speeds. He leveled off at 5,000 feet and began a series of gentle maneuvers, getting a feel for the aircraft's handling characteristics. Everything the combat reports had claimed about the Zero's agility proved true. The fighter turned inside imaginary opponents with ease, the controls remaining light and responsive throughout. Trapnell noted that the Zero could sustain turns at lower speeds than any American fighter he'd flown, a capability that explained how Japanese pilots had been able to position themselves on the tails of Allied aircraft with such apparent ease. But Trapnell was searching for weaknesses, not confirming strengths. As he pushed the Zero through increasingly aggressive maneuvers, he began to notice subtle characteristics that combat pilots might exploit. The aircraft's extreme lightness, while advantageous in turning fights, made it susceptible to rough handling. The control forces, so pleasantly light at low speeds, became increasingly sensitive as velocity increased. And there was something else. A peculiar stiffening in the aileron response as he pushed past 180 knots indicated airspeed. The first flight lasted 45 minutes, ending with a landing so gentle the Zero barely seemed to settle onto the runway. Trapnell climbed out with his mind already cataloging observations, preparing the detailed technical report that would guide subsequent test flights. He knew he'd only scratched the surface. The real evaluation would require pushing the Zero to its limits, exploring the outer edges of its performance envelope, where the aircraft's true character and its vulnerabilities would finally reveal themselves. 2nd of October 1942 marked the beginning of systematic high-speed testing that would expose the Zero's critical flaw. Commander Trapnell took the captured fighter aloft with a specific mission: determine the aircraft's handling characteristics across its entire speed range, from stall to maximum velocity. The morning air was crisp over San Diego Bay as Trapnell climbed the Zero to 15,000 feet, establishing an altitude buffer for the high-speed dives he planned to conduct. At this height, the thin air offered less resistance, allowing him to build velocity more rapidly while maintaining sufficient altitude for recovery should anything go wrong. Navy chase planes flanked him, their pilots ready to observe and document whatever transpired. Trapnell began conservatively, nosing the Zero over into a shallow dive and allowing the airspeed to build gradually. At 150 knots, the controls felt normal, light, responsive, predictable. At 170 knots, still normal. He pulled out of the dive, climbed back to altitude, and prepared for a steeper descent. The second dive was more aggressive. Trapnell pushed the nose down at a 20-degree angle, watching the airspeed indicator needle sweep clockwise. 180 knots, 190 knots. At 195 knots, he attempted a standard aileron roll to the left, a maneuver he'd performed thousands of times in various aircraft. The Zero responded beautifully, rolling crisply around its longitudinal axis. He recovered, climbed again, and prepared to test the roll in the opposite direction. This time, as the airspeed climbed through 200 knots, Trapnell initiated a roll to the right. The stick moved, but the aircraft barely responded. He applied more pressure, pushing the stick further right. Nothing. The Zero continued flying straight ahead as if its ailerons had suddenly been disconnected. Trapnell's pulse quickened, but his hands remained steady. He eased back on the throttle, allowing the airspeed to bleed off. At 190 knots, he tried the roll again. This time the aircraft responded, though sluggishly. At 180 knots, the roll rate returned to normal. He climbed back to altitude, his mind racing through possible explanations for what he'd just experienced. The phenomenon was repeatable. Over the next 30 minutes, Trapnell conducted multiple high-speed runs, each time encountering the same problem. Above approximately 200 knots indicated airspeed, the Zero could not execute a proper roll to the right. It would roll left without hesitation, but rightward rolls became progressively more difficult as speed increased, eventually becoming impossible at the aircraft's maximum velocity of around 330 knots. This wasn't simply sluggish control response, it was complete control reversal on one side only. Trapnell recognized immediately that he'd discovered something profoundly important. In combat, a pilot's ability to roll away from an attacker could mean the difference between life and death. If American pilots knew that a Zero pursuing them at high speed couldn't follow a hard roll to the right, they'd just been handed a tactical advantage that could neutralize the Japanese fighter's superiority in other areas. After landing, Trapnell immediately convened a meeting with the engineering team. Together, they developed a hypothesis. The Zero's exceptionally light construction, combined with aerodynamic forces at high speeds, was causing the right wing to twist under aileron load. When the pilot commanded a right roll by pushing the stick right, the right aileron deflected downward. At high speeds, the aerodynamic pressure on that deflected aileron was literally twisting the wing, counteracting the intended roll motion. This phenomenon, known as aileron reversal, wasn't unique to the Zero. American designers had encountered similar issues in other aircraft. But the Zero's extreme lightness and minimal structural reinforcement made it particularly susceptible. The Japanese had prioritized agility and range over structural strength, accepting trade-offs that their engineers either didn't fully understand or considered acceptable given the aircraft's intended mission profile. Trapnell's report, filed on 3 October 1942, included detailed airspeed data, control force measurements, and his professional recommendation. American fighters should engage Zeros in high-speed combat whenever possible, using diving attacks and rolling maneuvers to the right to evade pursuit. The document would be classified and distributed to fighter squadrons throughout the Pacific, ultimately saving countless American lives. 10th of October, 1942. The testing program expanded beyond simple flight evaluation to include mock combat scenarios that would prove revolutionary in developing effective counter-tactics. Commander Trapnell was joined by other experienced Navy pilots, including Lieutenant Commander John Thatch, the tactician who had already developed the Thatch-Weave defensive maneuver based on fragmentary intelligence about Zero capabilities. Thatch approached the captured Zero with the enthusiasm of a chess master studying an opponent's strategy. He'd spent months analyzing combat reports, interviewing survivors, and theorizing about how to overcome the Zero's advantages. Now, he could test his theories against the actual aircraft, flown by American pilots who understood both machines intimately. The mock combat trials pitted the Zero against a Grumman F-4F Wildcat, the Navy's primary carrier-based fighter. On paper, the matchup appeared hopelessly one-sided. The Zero could outturn the Wildcat at any speed, outclimb it to altitude, and operate at ranges the American fighter couldn't match. Yet the actual combat trials revealed a more nuanced picture. When fighting defensively, trying to shake a pursuing Zero, the Wildcat pilot discovered that diving away while executing hard rolls to the right caused the Zero to lose tracking almost immediately. The Japanese fighter simply couldn't follow the maneuver at speeds above 200 knots. This single tactic transformed the engagement dynamics. What had been a death sentence for Wildcat pilots suddenly became a reliable escape maneuver. Thatch documented another critical weakness during these trials. The Zero's lightweight construction, while enabling extraordinary maneuverability, made it structurally fragile compared to American fighters. The Wildcat could survive punishment that would tear a Zero apart. Thatch observed that even relatively light-caliber weapons fire could catastrophically damage the Japanese fighter, particularly since it lacked self-sealing fuel tanks, another weight-saving measure that left Zero pilots vulnerable to fire. Testing also revealed the Zero's superior vision from the cockpit. The bubble canopy provided excellent visibility in all directions, a significant advantage in combat where spotting the enemy first often determined the engagement's outcome. American fighters of that period featured heavier framing and more limited rearward visibility, putting their pilots at a disadvantage in visual detection. Lieutenant Commander James Flatley, another test participant, focused on energy management, the art of maintaining and regaining airspeed during combat. He discovered that while the Zero excelled in sustained turning fights, it bled energy rapidly in vertical maneuvers. An American pilot who avoided prolonged turning engagements and instead used boom and zoom tactics, diving from altitude, firing a quick burst, then climbing away, could engage effectively without playing to the Zero's strengths. According to documentation from the Naval Aviation History Office, these mock combat sessions produced the first comprehensive tactical doctrine for fighting Zeros. The guidelines were straightforward. Never dogfight a Zero below 300 knots. Always maintain speed advantage. Use diving attacks whenever possible. If pursued, dive away while rolling right. Concentrate fire to achieve kills quickly, as Zeros are fragile, and fight in pairs using mutual support tactics. The intelligence value extended beyond pure tactics. Engineers carefully documented every aspect of the Zero's construction, from the hand-formed wing ribs to the fabric-covered control surfaces. They discovered that Japanese manufacturing emphasized craftsmanship over mass production efficiency. Each Zero was essentially hand-built by skilled workers. This explained both the aircraft's quality and Japan's difficulty in producing them in quantities matching American output. Metallurgical analysis of the Zero's aluminum alloy skin revealed another surprise. The Japanese had developed a proprietary alloy called extra super duralumin that provided excellent strength-to-weight ratios but was more brittle than American alternatives. This material choice contributed to the Zero's structural weaknesses while enabling its remarkable lightness. The engine, that 950 horsepower Nakajima Sakai radial, received particular attention. American engineers marveled at its smooth operation and excellent power-to-weight ratio. However, they noted that it lacked the robust construction of American power plants like the Pratt & Whitney R2800. The Sakai was optimized for efficiency and weight rather than durability, another trade-off that reflected Japanese design philosophy. By mid-October, the test program had generated thousands of pages of technical data, tactical recommendations, and intelligence assessments. This information was rapidly disseminated throughout the Pacific Fleet, fundamentally changing how American pilots approached combat with Japanese fighters. 23rd of October 1942, a classified briefing at Pearl Harbor brought together squadron commanders from across the Pacific Fleet to review the findings from the captured Zero tests. What they learned would revolutionize American fighter tactics and begin shifting the balance of air superiority in the Pacific theater. Commander John Smith, Jimmy Thatch, stood before the assembled pilots with unprecedented confidence. For the first time since the war began, he could speak with authority about the enemy's capabilities based on empirical data rather than desperate speculation. The captured Zero had stripped away the mystique that had surrounded Japanese aviation, replacing fear with understanding. The briefing began with film footage from the mock combat trials. Pilots watched as the Zero effortlessly outturned a Wildcat in a traditional dogfight, confirming what they'd experienced in actual combat. But then, the footage showed something new. The Wildcat pilot pushing into a high-speed dive, rolling hard right, and watching the pursuing Zero fall away, unable to follow. The room erupted in animated discussion. Thatch explained the aileron reversal phenomenon in terms combat pilots could immediately understand and apply. Above 200 knots, he emphasized, the Zero became a different aircraft, still dangerous, but no longer invincible. The key was maintaining energy and speed, never allowing the engagement to devolve into a slow-speed turning contest where the Zero's advantages became overwhelming. Lieutenant Edward O'Hare, present at the briefing, contributed insights from his own combat experience. He'd engaged Zeros over the Lexington back in February, before anyone understood the enemy fighter's characteristics. Looking back, he realized his survival had depended on instinctive tactics that aligned with the test findings, maintaining speed, using surprise, and breaking off before the Zero could leverage its turning ability. The briefing also addressed psychological factors. Many pilots had developed an almost superstitious dread of the Zero, viewing it as an unbeatable opponent flown by superhuman pilots. The test data helped dispel these myths. Yes, the Zero was an exceptional aircraft in certain regimes, but it had clear limitations. Japanese pilots were well trained but not invincible. The war could be won through superior tactics and by exploiting known weaknesses. Fighter squadrons immediately began adapting their training programs to incorporate the new tactical doctrine. At Maui's Punene airfield, Marine Corps pilots practiced high-speed diving attacks and rolling escapes until the maneuvers became second nature. At Henderson Field on Guadalcanal, where American forces were locked in desperate combat for control of the Solomon Islands, the tactical bulletins arrived like salvation. Major John Lucian Smith, commanding Marine Fighting Squadron 223 at Guadalcanal, implemented the new tactics within days of receiving the briefing materials. His pilots had been suffering heavy casualties against Zero-equipped Japanese units. Now, they had a fighting chance. Smith emphasized discipline, resist the temptation to dogfight, maintain altitude and speed advantages, work in pairs, and always have an escape route planned. The results were immediate and dramatic. Marine pilots who had struggled to survive encounters with Zeros began scoring kills. The tactics worked exactly as predicted. Diving attacks delivered at high speed gave the Zeros no opportunity to respond effectively, while right-rolling escape maneuvers frustrated Japanese pilots who found their aircraft inexplicably unable to follow. Historical records from the Marine Corps Aviation Association document the transformation in kill ratios during late 1942. Prior to the tactical revolution, American pilots were losing exchanges with Zeros at approximately 3-to-1 ratios. By November, after widespread implementation of the new tactics, those ratios had reversed. American pilots were now shooting down 3 Zeros for every friendly aircraft lost. The psychological impact matched the tactical success. American pilots entered combat with renewed confidence, knowing they possessed specific techniques that could neutralize the Zero's advantages. This confidence translated into aggressive, effective tactics that kept Japanese pilots on the defensive. Japanese commanders noticed the shift in American tactics and struggled to understand what had changed. Their intelligence services never discovered that the Americans possessed an intact Zero for testing, so they couldn't warn their pilots about the specific vulnerabilities being exploited. Japanese pilots continued flying the only way they'd been trained: aggressive, close-in dogfighting, walking directly into the trap that American tacticians had designed. The broader implications extended beyond individual combat. American aircraft designers, now understanding exactly what made the Zero effective, could incorporate those lessons into next-generation fighters. The need for better visibility, lighter control forces at low speeds, and improved maneuverability became design priorities. The Zero had been teaching American aviation how to build better fighters. 5th of November, 1942. Engineers at Naval Aircraft Factory in Philadelphia received detailed technical drawings and specifications derived from the captured Zero, beginning a comprehensive analysis that would influence American aircraft design for the remainder of the war. The engineering team, led by Commander Ralph Wood, approached their examination with systematic thoroughness. Every component was measured, weighed, tested, and compared against equivalent American parts. What emerged was a portrait of radically different design philosophies between Japanese and American aviation engineering. The Zero's wing structure revealed extraordinary ingenuity. Japanese engineers had created a wing that was simultaneously strong enough to withstand combat maneuvers, yet light enough to provide exceptional performance. They achieved this through careful material selection and innovative structural design. The main wing spar consisted of a single piece of forged aluminum, machined to varying thicknesses, that provided maximum strength exactly where needed, while minimizing weight elsewhere. American engineers had favored simpler, more robust designs that could be manufactured quickly by semi-skilled workers. The Zero's wing, by contrast, required skilled craftsmen and time-consuming hand-fitting. This explained why Japan struggled to mass-produce Zeros at rates matching American aircraft output, but it also demonstrated what could be achieved when engineering elegance trumped manufacturing efficiency. The control surface design particularly intrigued the American team. The Zero's ailerons featured ingenious balance tabs that reduced control forces across most of the flight envelope. However, these same design choices contributed to the aileron reversal problem at high speeds. The American engineers recognized a lesson. Optimizing for one flight regime inevitably creates compromises in others. The Zero was optimized for combat below 250 knots, and its designers had apparently accepted degraded high-speed handling as an acceptable trade-off. Testing of the Zero's aluminum alloy skin revealed impressive material science. The extra super duralumin alloy achieved strength-to-weight ratios that American metallurgists couldn't match with their standard 2024 aluminum alloy. However, the Japanese material was more brittle and more susceptible to fatigue cracking. Again, trade-offs. The Zero gained immediate performance advantages at the cost of long-term durability. The engine analysis provided perhaps the most valuable intelligence. The Nakajima Sakai 14-cylinder radial was disassembled completely, with every component measured and analyzed. American engineers marveled at the quality of Japanese engine manufacturing. Precise tolerances, excellent metallurgy, and sophisticated engineering. The Sakai produced more power per pound than comparable American engines, though it achieved this partly by operating at higher temperatures and stresses that reduced engine life. Fuel system examination revealed a glaring vulnerability that combat pilots could exploit. The Zero's fuel tanks lacked self-sealing bladders, a weight-saving measure that left the aircraft catastrophically vulnerable to incendiary ammunition. Even a few rounds through a fuel tank could set a Zero ablaze. American engineers calculated that adding self-sealing tanks would have increased the Zero's weight by approximately 200 pounds, a seemingly modest penalty that Japanese designers had deemed unacceptable, given their obsession with minimizing weight. Documentation from the Smithsonian National Air and Space Museum archives indicates that the captured Zero directly influenced the design of the Grumman F-6F Hellcat, the fighter that would ultimately dominate Pacific skies. Grumman engineers studied the Zero's excellent visibility, light control forces, and maneuverability, then designed the Hellcat to match those characteristics while retaining American strengths in durability, firepower, and high-speed performance. The engineering team also examined the Zero's armament. 2 7.7mm machine guns in the nose and 2 20mm cannons in the wings provided a potent combination of rapid-fire volume and heavy hitting power. However, the cannons had limited ammunition, just 60 rounds per gun, forcing Japanese pilots to make every shot count. American fighters, by contrast, typically carried more ammunition and accepted the weight penalty for sustained firepower. Even the cockpit layout revealed cultural and practical differences. The Zero's instrument panel was sparse and efficiently organized, with everything a pilot needed and nothing he didn't. American cockpits tended to be more cluttered, with redundant instruments and additional equipment. The Japanese approach reflected a philosophy of elegant minimalism, while American designers favored redundancy and comprehensive information. By late November, the engineering analysis was complete. The final report ran to several hundred pages, documenting every aspect of the Zero's design with meticulous detail. Copies were distributed to every major American aircraft manufacturer, providing a comprehensive template of what worked and what didn't in fighter design. The captured Zero had become an involuntary professor, teaching American aviation the lessons that would ultimately help defeat it. 12th of December, 1942. Specialized tactical bulletins based on the Zero testing began arriving at forward airfields throughout the Pacific, from Darwin, Australia, to the Aleutian Islands. These documents, classified secret, and marked for pilots' eyes only, would transform combat operations across the entire theater. The bulletins didn't simply list the Zero's weaknesses, they provided specific tactical sequences that pilots could rehearse and execute under combat stress. Each maneuver was described with precise airspeed ranges, altitude recommendations, and step-by-step procedures. The Navy and Marine Corps had essentially created an instruction manual for defeating the previously invincible Japanese fighter. At Henderson Field, Guadalcanal, where American forces fought daily for control of the skies above the crucial island, the tactical bulletins arrived during a particularly desperate phase of the campaign. Marine and Navy pilots had been flying continuous missions against numerically superior Japanese forces, suffering losses that threatened the entire Guadalcanal operation. The new tactics offered hope at a critical moment. Major Robert Gaylor, commanding Marine Fighting Squadron 224, gathered his pilots for an intensive briefing. Many were exhausted from weeks of combat, some wounded, all carrying the psychological weight of friends lost to Zero fighters. Gaylor's message was direct. "We've been fighting the Zero on its terms. That ends today. From now on, we control the engagement." The pilots practiced the new tactics during rare moments between combat missions. They'd climb to altitude, simulate diving attacks, practice high-speed rolls to the right, and rehearse the discipline required to resist dogfighting. The training was rudimentary. There was no time for elaborate exercises, but the principles were clear enough that even tired pilots could grasp them. The first major test came on 17th of December, when a large Japanese raid approached Guadalcanal. 24 Zeros escorted bombers targeting Henderson Field, anticipating the usual furious but ineffective resistance from American fighters. Instead, they encountered a disciplined formation of wildcats that dove from altitude, made quick firing passes, then rolled right and dove away before the Zeros could respond effectively. The engagement lasted barely 10 minutes, but the results shocked Japanese pilots. 5 Zeros were shot down without a single American loss. An unprecedented outcome. Japanese after-action reports from that day, captured later in the war, revealed confusion and frustration. Their pilots reported that American fighters had somehow learned to disappear during combat, evading with maneuvers the Zeros couldn't counter. Throughout the Pacific, similar stories began accumulating. In New Guinea, P-39 Airacobra pilots, flying a fighter generally considered inferior to the Zero, implemented the new tactics and found themselves competitive. In the Aleutians, where American and Japanese forces still skirmished over the occupation of Kiska and Attu Islands, the tactical advantage shifted decisively toward the Americans. Lieutenant Colonel Harold Bauer, a Marine Corps ace, contributed his own innovations to the tactical doctrine. He emphasized formation discipline, arguing that lone wolves, individual pilots hunting for personal glory, would still fall victim to Zeros despite knowing the correct tactics. Two fighters working in pairs, covering each other and executing coordinated attacks, could dominate larger numbers of Zeros through superior tactics and mutual support. The thatch weave, that defensive maneuver developed earlier in the year, became even more effective when combined with the new understanding of Zero limitations. When a pair of American fighters flew the weave correctly, crisscrossing paths to create overlapping fields of fire, they could defeat Zero attacks while maintaining the speed necessary to exploit the Japanese fighters' high-speed handling weaknesses. Statistical analysis compiled by Navy intelligence in early 1943 showed the tactical revolution's impact. During the first 6 months of the Pacific War, American pilots had achieved approximately 0.5 kills per loss against Zero-equipped units, meaning they lost 2 fighters for every Zero destroyed. By early 1943, that ratio had improved to approximately 2.5 kills per loss, a 5-fold improvement in combat effectiveness. These statistics represented more than abstract numbers. Each improved kill ratio meant American pilots returning safely, experience being retained, and morale improving. The psychological transformation was as important as the tactical one. American pilots no longer feared the Zero. They hunted it with confidence born from understanding. Japanese commanders recognized something had changed, but couldn't identify the cause. Their intelligence services reported that American pilots seemed better trained and more disciplined, but the reports missed the fundamental truth. The Americans had stolen the Zero's secrets and turned them into weapons. Every tactical bulletin distributed to American squadrons represented knowledge purchased with Koga's life and extracted from his aircraft through Commander Trapnell's skilled evaluation. 28th of February, 1943. The tactical and strategic situation in the Pacific had transformed so dramatically that Japanese naval aviation commanders gathered at Rabaul to discuss their declining effectiveness. They didn't yet understand that a single captured Zero had precipitated their reversal of fortune. The decline manifested in multiple dimensions simultaneously. American pilots, now confident in their tactics, flew more aggressively. Japanese pilots, experiencing unprecedented losses, became more cautious. The psychological balance had shifted, and once air combat psychology tips in one direction, it becomes self-reinforcing. Aggressive pilots gain more opportunities. Cautious pilots cede initiative. Fighter sweeps over the Solomon Islands, once dominated by Japanese Zeros, increasingly resulted in American victories. The new Grumman F-4U Corsair, incorporating lessons learned from the captured Zero, began appearing in Marine Corps squadrons. This powerful fighter combined American firepower and durability with improved maneuverability and excellent high-speed handling. When flown according to the tactical doctrine developed from Zero testing, the Corsair proved devastatingly effective. Japanese aircraft designers, meanwhile, were developing the Zero's successor, the Mitsubishi J2M Raiden, but production delays and technical problems prevented its widespread deployment. The Zero, originally designed in 1939 for a different kind of war, had to soldier on against increasingly sophisticated opposition and pilots who understood exactly how to exploit its weaknesses. The captured Zero at North Island continued serving as a training aid throughout 1943. New pilots arriving in the Pacific Theater would often receive orientation flights in or against the Japanese fighter, experiencing firsthand how it handled and where its limitations became apparent. This experiential learning proved invaluable, far better than reading bulletins or attending lectures. Additional captured Zeros arrived in American hands as the war progressed, though none proved as influential as Koga's aircraft. The subsequent captures confirmed what testing had already revealed, and allowed more detailed study of variations between different Zero models. Some captured Zeros were sent to Army Air Forces bases, allowing P-38 Lightning and P-47 Thunderbolt pilots to develop tactics specific to their aircraft. Intelligence from the captured aircraft extended beyond pure combat tactics. Understanding the Zero's range capabilities helped American commanders anticipate where Japanese forces could operate from. Knowledge of its maintenance requirements and reliability issues informed planning for extended campaigns. Even small details, like understanding how long it took to restart the Sakai engine after shutdown, provided tactical advantages in specific situations. By mid-1943, the strategic implications of the tactical revolution became clear. American forces could contest airspace that had previously been Japanese-dominated. This enabled more aggressive offensive operations, better protection for shipping and amphibious landings, and ultimately accelerated the Allied advance across the Pacific. The air superiority equation had fundamentally changed. Historical documentation from the National Museum of the Pacific War notes that Japanese aviation never recovered from this reversal. While they developed new fighters and tactics, they could never regain the psychological and tactical advantage they'd enjoyed in the war's early months. American pilots had learned the lessons the captured Zero taught, and those lessons were institutionalized in training programs that continued producing well-prepared pilots throughout the war. The human cost of this transformation was measured in lives saved rather than lives lost, inherently difficult to quantify, but nonetheless real. How many American pilots survived combat because they knew to roll right above 200 knots? How many successful missions resulted from confident, aggressive tactics enabled by understanding the enemy? The captured Zero's influence permeated every aspect of Pacific air combat. Koga Zero was eventually retired from active testing in late 1943, having served far beyond its intended lifespan. The aircraft had accumulated hundreds of flight hours in American hands, more than many Zeros achieved in Japanese service. It had been examined by countless engineers, flown by dozens of pilots, and contributed to intelligence briefings that reached thousands of aviators. The aircraft's final disposition reflected its historical significance. Rather than being scrapped, it was preserved for potential future display, though wartime priorities meant it would spend years in storage before finally being recognized as the invaluable artifact it had become. 15th of August, 1945. As Emperor Hirohito's surrender broadcast echoed across Japan, American intelligence officers began compiling comprehensive assessments of what had contributed to Allied victory. The captured Zero consistently appeared near the top of every list, its intelligence value recognized as potentially war-winning. The strategic impact of that single aircraft recovered from Akutan Island exceeded any reasonable expectation. It had revealed enemy capabilities, enabled tactical innovations, influenced aircraft design, and transformed combat psychology. all stemming from one fortunate capture and the skilled analysis that followed. Historians would later debate whether any other single intelligence coup in the Pacific War yielded comparable strategic benefits. Commander Frederick Trapnell, the test pilot who first discovered the Zero's aileron reversal problem, survived the war and continued his distinguished career in naval aviation. He rarely spoke publicly about the Zero testing, bound by classification restrictions that persisted long after the war ended. But within naval aviation circles, his contribution was understood and appreciated. He had turned enemy technology into American advantage through skilled piloting and analytical insight. Flight Petty Officer Tadayoshi Koga, whose death enabled the capture of his aircraft, was never forgotten by Japanese naval aviation. His sacrifice, unintended though it was, had inadvertently provided the enemy with priceless intelligence. In Japanese accounts of the war, Koga's fate represents the cruel ironies of combat, where individual tragedies can cascade into strategic consequences that affect thousands. The captured Zero itself faced an unfortunate end despite its historical significance. After years in storage, it was being prepared for restoration and display at the National Air and Space Museum when, on 11th of July, 1978, it was destroyed in a transportation accident. The loss of this irreplaceable artifact was mourned by aviation historians and veterans who understood its true significance. However, the lessons it taught survived. The tactical doctrines developed from testing Koga's Zero influenced American fighter tactics for decades. The principle of understanding enemy capabilities through direct evaluation became institutionalized in military intelligence gathering. Every captured aircraft, every enemy weapon system evaluated, followed procedures pioneered during the Zero testing program. The engineering insights proved equally enduring. American aircraft designers who studied the Zero carried those lessons into the jet age. The emphasis on pilot visibility, control harmony, and optimizing performance across the entire flight envelope, all lessons reinforced by Zero analysis, became fundamental principles in fighter design. The North American F-86 Sabre, the fighter that would dominate Korean war skies, reflected engineering philosophy shaped partly by understanding what made the Zero effective and where it fell short. Veterans who fought Zeros with tactics derived from the captured aircraft's testing often didn't know the source of their survival. The classified bulletins they received never mentioned Akutan Island or Koga's name. They simply knew that someone, somewhere, had figured out how to beat the Japanese fighter, and that knowledge had saved their lives. Only decades later, as documents were declassified and histories written, did the full story emerge. The intelligence community studied the Zero operation as a case study in exploitation of captured enemy equipment. The rapid recovery, careful preservation, systematic testing, and effective dissemination of findings became a template for future operations. When American forces captured German jet fighters near the end of the European War, the procedures followed closely resembled those pioneered with Koga's Zero. Japanese aviation historians, examining their nation's defeat, identified multiple factors that contributed to losing air superiority. Industrial production disadvantages, attrition of experienced pilots, fuel shortages, and increasingly sophisticated American aircraft. But they also acknowledged that American tactical innovations in 1942 and 1943, innovations directly traceable to the captured Zero, accelerated their decline beyond what material factors alone would have caused. The personal stories of pilots who survived because of tactics derived from Zero testing could fill volumes. Lieutenant Junior Grade Alexander Vrashu, who became the Navy's fourth-ranking ace with 19 kills, employed the high-speed diving attack and rolling escape maneuver repeatedly throughout his combat career. He credited his survival to training that emphasized exploiting enemy weaknesses rather than engaging in prolonged dogfights. Major Gregory Boyington, the legendary Marine Corps ace who commanded the Black Sheep Squadron, was known for aggressive tactics that nonetheless adhered to the fundamental principles discovered through Zero testing. His philosophy of maintaining energy advantage, working in pairs, and avoiding the enemy's strengths while exploiting his weaknesses perfectly embodied the lessons that Trapnell had first documented in October of 1942.